Thank you. Actually, just before I start, I just need to pour this in here. So just add that to there. That's it. Good. Actually, I'll give that. Thank you. Right. So now the idea behind this lecture is that I wanted to do a lecture with lots of bangs and flashes, but without using any chemicals. Because, of course, chemicals seem to have a bad name, and this is not really fair. So people think that chemistry is all about sort of making nasty, polluting, evil chemicals. But what I want to try and show is that, well, everything around us is all made of chemicals. We are made up of chemicals. The food we eat, the clothes we wear, the air we breathe, all of these things are natural chemicals. And we shouldn't be frightened of the word chemistry. Okay, without it, well, we wouldn't be able to stay alive. So there are lots and lots of chemicals that are known. I mean, here are some. There's some good names. Oops, some good names here. Look. So how about this? We've got 2-acetyl 5-methylfuran, or 2-ethyl 6-methylpyrazine, or one down the bottom there, 2-methyl tetrahydrothiamphenthreone. Okay, really complicated sounding things, aren't they? Now, I'm about to do something, though, that you should never, ever do in a laboratory. I'm going to drink all of those chemicals. That's very, very bad. You wouldn't normally do this. So I've put them all into this, receptacle here, and I'm just going to drink them. Well, actually, this is, of course, just a cup of coffee. And all of these chemicals here have been detected in coffee. In fact, over 2,000 different compounds have been detected in coffee. Okay? And one of them is shown on here. Does anyone have a guess? Anyone want to guess what this one might be? Does anyone know a chemical that you might find in coffee? Yep. Anyone want to shout it out? Caffeine, yes. Somebody's a very good chemist. You clearly recognize the chemical structure here. I'm very, very impressed. But yes, caffeine is just one of those compounds that we can find in our coffee. Okay? But there's all these other ones, and I say around 2,000 others that have been detected. So each one of these peaks, this is an analysis of the aroma coming off of coffee. Each one of these peaks corresponds to just one chemical that has been detected in the analysis there. Okay, so many, many different chemicals in here. Now, this is caffeine, the one right at the top there that you instantly recognized. I was very impressed with that. But these are just a few of the other structures. Okay, so now the grey atoms that you see there, well, they represent carbon atoms. The white are hydrogen, red are oxygen, blue are nitrogen, and the yellow one down the bottom there, well, that's sulfur. So we have different elements bound together to give these, well, rather complicated structures. Okay, but each one of these is different. And we're going to be looking at some of these. Well, some of them aren't really very nice that we find. All of these are from our coffee, but some of them aren't very nice. The one at the top there is called Pyridine, and that smells really not very pleasant at all, and it makes you go sterile, so that's not very nice. You wouldn't really want to drink too much of that. The two with the blue nitrogen atoms on the ends, well, they're called putrescine and cadaverine. So they're not very nice names. So putrescine sounds really disgusting here, and cadaverine, well, that's a cadaver is a dead body. Both of these two give us a smell of decaying flesh. Horrid, horrid. But then it's in coffee as well. And we have the one with the yellow there. That's even worse. That one smells really disgusting. Methane thiol, that's called. And it's really, it smells worse than rotten eggs. It's one of the worst smells you can imagine. And that's actually also found in human feces. But anyway, it's still in the coffee. And that's what makes it all taste so yummy. Now, of course, when we're making our coffee, though, maybe you haven't considered this, but what you're doing chemistry. Because we're extracting the nice ones that we want, that taste good, from all the bits that we don't want, all those crusty rinds and so on. That's all staying in the top here. We're filtering it out, we're extracting it with water, we're dissolving the ones we want in the water, letting them filter through and collecting those. That's the sort of things that the chemists routinely do every day when they're making new compounds. So you are doing chemistry just when you make a cup of tea or a cup of coffee. Okay? These are the sort of things. We're extracting what we want, leaving behind what we don't want. Well, I've got one more little demonstration using some of the chemicals that have been detected in coffee. These are some of the, well, nicer ones. The nicer one there is the one in the middle on the right-hand side, and that's called vanillin. And this you actually find in vanilla. So the nice smell of vanilla ice cream and so on, that's due to this compound there. That's one of the ingredients you would find there. This is quite nice, but we've combined that with one of the other chemicals that's been detected. This is in the centre there, the one with 4 red oxygen atoms connected to the 2 carbons. This is called oxalic acid. And this you can find in particularly strong in rhubarb leaves. Okay, so it's rather sharp. You shouldn't eat them because it's rather toxic. But we've reacted those two together, okay, and we've made a new compound. Well, actually, I say we, but Craig has done this, and Craig is standing over here. He spent all day doing this. So we've dissolved this in a solvent, and this is what we've got here. So this is our vanillin combined with the oxalic acid. Okay, we've dissolved it in a solvent, and this solvent is called ethyl ethanoate, and that's the one right on in the bottom corner there. And I'm going to add, well, another one of the compounds that's been detected called Pyridine. That's the one at the top with the 5 rings together. So I'm just going to mix that one in. Okay, that's nice. I'm going to add some sodium hydroxide. This is just an alkali solution. Okay, that's that. And actually, maybe can we just have the lights down for a second, please? I'm going to have the last ingredient, which is hydrogen peroxide, and then we'll see if any change takes place. Look at that, chemiluminescence. So this is light from chemistry, and all of this from the ingredients that you can find in coffee. Amazing. So, lots of chemicals there. In fact, even the filter paper itself, the paper that we're filtering this coffee through, I mean, that's a chemical as well. It's made of cellulose. This is the structure of cellulose. It's long fibres where we have lots of little rings all joined together. Well, each one of those rings is a molecule of glucose that we join together, that's joined together to make up the cellulose. Glucose is very important. It gives us our energy. It's in our blood. Okay, that's what's racing around our bodies, providing our energy. So these rings are all joined together there, and that's what makes up the fibres of the paper in the cellulose. But these rings, these little glucose rings, they crop up in all sorts of different places. And you can spot them, if you're careful, in this. This is the structure of one of the pigments that you can find in these beautiful purple cabbages. Okay? So these are called anthocyanins, and these pigments are responsible for many of the colours that we have in certain fruits and vegetables. So, for instance, I mean, well, the roses are red because of anthocyanins, or eggplants are purple because of these anthocyanins. Okay, so they're really, really common in nature, these pigments. And what they have in common are those 3 rings at the top, and then there are different bits sticking onto the rings. And these ones have, well, they're 2 glucose. That's where the glucose rings are, the things at the bottom there, those messy bits down the bottom. But these are stuck onto the 3 rings at the top, and I say responsible for many, many pigments that you can find in nature. Now, these have some really interesting properties, and this is when we alter the acidity of the water. So we can do this with some acid. So you know that vinegar is very sharp, or lemon juice is very sharp. Well, we're going to do this. I'm going to add some acid to our cabbage water. So all we have here is just some water with, that we blended with a cabbage. Just going to add a little bit of acid, and it goes instantly red. Okay, so this shows, it indicates the presence of the acid here. So we'd say that this compound acts as an indicator. Okay, we'll leave this one as it is. I'm going to add, well, this is some lime water or calcium hydroxide. I'm going to add that, a little bit of that to this one. And this should go as sort of a bluier colour. Okay, that's sort of getting there. I'll add a bit more to this one, I think. And we get quite a green colour for this one. So we've got red, purple, blue, green, and then this final one I'm going to add, well, this is also an alkali, like the calcium hydroxide, and that means, well, it's the opposite of an acid. So acids give hydrogen ions these ones, well, they mop up any hydrogen ions that might be in there. So this is certainly quite light green to start off with, and I'm hoping that if we just leave it a little bit, it might go actually quite yellow. So we'll have to keep an eye on that one and see what it looks like in a little bit. It's certainly getting lighter and lighter. But this is where we're just changing the structure slightly of this molecule here, this anthocyanin dye. We're just sticking on these little hydrogen ions, just one atom, sticking on these or taking them off, and maybe even opening up the structure. And that changes it, and it changes how it interacts with light and gives us these different colours here. So we're going to use this through the lecture. We'll be able to tell if something is acidic, because it will change the cabbage water red, or if it's the opposite of an acid, if it's alkaline, and it'll change it, well, either green or possibly even sort of a yellowy colour. Okay, so we'll be using this cabbage water in the lecture. Now, this is quite a complicated structure, though, this one, with well, it's got carbon, hydrogen, and oxygen all bonded together, but they needed to be bonded together in just the right way to give it its special properties. But we can actually find the individual elements themselves. So carbon or oxygen, of course, I mean, oxygen we breathe in all the time. That's not combined with any other elements, it's just by itself. But carbon we can also find lying around. In fact, here's a piece here. Well, this is an impure piece of carbon. It's actually charcoal. This is used to be wood. We've heated it up and driven out a lot of the volatile materials, some of the water and so on, and some of the other volatile things that it contains, but we haven't burnt it completely, so this is, well, it's impure form of carbon. So that's pretty much almost, an element, carbon there, but I say there's some impurities in there as well. But there are other elements that we can find lying around. I mean, this is some metal, this is copper. If we're lucky, we might be able to find some copper lying around, and there are a few other elements that we can find as well, but we'll have a look at some of these in the course of the lecture. Sometimes with our metals, we can't find the pure metal. So for instance, iron. Well, iron we don't normally find just lying around. This is a piece of iron, but of course if I left this lying around outside, well, what would happen to it? What would happen? Anyone to shout out? Yep. Well, it will rust, yes, exactly, it will change. Well, it will change and it will end up looking like this. This is one that has been rusted up and we've cut it open, but it's gone very rusty. A chemical change has taken place here as the iron reacts with, well, any oxygen and water from the air, and a change takes place and it's converted from the iron here to this iron compound, this iron oxide. Well, you can occasionally find bits of iron. I said you can't really find it, and one way to find it is if you're lucky enough to find certain meteorites that have fallen to the earth. Okay, but again, these come to the earth and they just can be lumps of iron, but again they will react with the oxygen from the atmosphere and they will gradually change and they will become rusty, and then you won't have a nice iron meteorite any longer. Well, I thought I might show you this reaction, the reaction of iron combining with oxygen, and why you can't really just find iron lying around. So I have some iron here, and this is iron wool. So it's just the sort of thing that you might use to sort of clean your pots and pans. I'm going to add to this some oxygen. Well, of course, there's oxygen all around us in the air that we breathe, but this is liquefied oxygen. So oxygen is normally a gas, but here we've cooled it down to make it into a more concentrated form. So I'm just pouring this very, very cold liquid oxygen onto the iron wool here, and it's instantly turning back into the gas, but it's just ensuring that there's lots of oxygen vapor, lots of oxygen gas around our wool here. Now, if we just have the lights down, I'm just going to apply a light and see what happens. Wow, so you can certainly see that a lot of energy has been given out there. In fact, I can warm my hands here quite nicely. It's very, very warm now. But this shows that energy has been released as the iron combines with the oxygen. And this is a very, very important point in chemistry, that energy is given out as we make chemical bonds. So we could write an equation, a chemical equation for what's just taken place there. The iron has combined with the oxygen that we added, and that's formed a new compound, iron oxide. And that's what we've got here. But during the formation there, a lot of energy is released, okay, which is very, very important. But this is how we will find our iron in nature, not as iron metal, but as combined with other elements such as oxygen. So in fact, this is the mineral hematite, okay? And it looks just like a sort of piece of rusty metal, really. Well, in a sense it is. This is iron oxide, so iron combined with oxygen. And this is a nice polished up piece here, Okay? So this is how we would normally find our iron, not as iron metal, but as a mineral from which we would have to extract the iron if we wanted to get it out. Okay? Well, it's not just oxygen that can react with iron. There are other elements as well, such as the element sulfur. And I have some sulfur in here. So the sulfur is the yellow powder down the bottom, and at the top here we've got some iron powder. And it's just held on with a magnet at the moment. I'm just going to release that and shake it up, mix it up. Right, and I'm going to, thank you, heat this up in a moment. Thank you. So this is my iron mixed up with the sulfur. And I'm going to heat this, and we'll see if we can get a chemical reaction to start. So before we had iron combining with oxygen, now we're going to try iron combining with sulfur. And again, maybe if I have the lights down, please. So I'm just warming up the bottom of the tube. Okay, now it's just beginning to glow, and you can see that this glow is spreading through the whole of the mixture. It's all becoming red hot, not because I'm heating it, I've stopped heating it, but it's because of the reaction taking place as the iron is combining with the sulfur, and it's again giving out a lot of energy as we're making the new iron-sulfur bonds. Okay. So this is another way in which we can find our iron, not just by itself, but combined with, well, maybe sulfur. And I have some down the front here. This lovely mineral here, this nice shiny gold-coloured mineral, well, it's fool's gold. It's not real gold at all. But fool's gold is made up of iron combined with sulfur. So fool's gold is also known as iron pyrites, and the chemical formula for this would be Fe, that stands for the iron, S2. This means that for every one atom of iron we have, it has 2 atoms of sulfur locked in, bound into it. So this is our fool's gold. Now I'm going to take some of this, going to take a piece of fool's gold, and we're going to smash it up with a hammer. Okay? So I'm going to take it over to my anvil, my handy anvil over here, and smash it up. So it's quite easy to sort of powder, and just going to tip some of this into this tube here. Some of the bits. So here's my fool's gold, my iron pyrites, and now I'm just going to heat this up. Okay? So this is our mineral. This is one of the ways that we could find iron and sulfur combined together. So I'm just going to heat this up, and we should see a chemical change take place. Now, so the chemical formula for the iron pyrites, or the fool's gold, is FeS2. The structure for this, if we looked at where all the atoms are, well, this is what we would see. The grey spheres represent atoms of iron, and the yellow spheres represent atoms of sulfur. And there's twice as much sulfur in here as there is iron. But what I'm trying to do now is heat up this and see if I can break it down a little bit. Okay? So now before, the 2 reactions that you've seen where the iron combines with the oxygen or the iron combined with the sulfur, well, that gave out a lot of energy. In this one, I need to put a lot of energy in. I'm just heating this up. It needs to be very, very hot. And I need to heat it up to break the bonds that we have here. So I'm trying to break the chemical bonds between the iron and the sulfur. And I'm hoping that we might see some of the sulfur come out of this compound. And you may be able to see a yellow colour developing round the cooler parts of the tube. And this yellow colour is sulfur. So what we're doing here, we're heating up the iron pyrites and driving out some of the sulfur, and that's the yellow colour that you can see here. Okay, now it's gone black, so it's not nice shiny gold colour any longer, it's a black colour. But we've partially broken it down to give iron sulfide in the bottom and driven out some of that extra sulfur there. So that's one way that we could get some sulfur. Right? So we could get our sulfur from minerals like the iron sulfide, like the iron pyrites. We could drive it out. But you can also find sulfur just lying around. In fact, here's a piece here. And this piece comes from Indonesia, from Java, okay, which is rather nice. So this is a little lump of sulfur. And I have a slide here showing some more sulfur. This is on an island just off of the coast of Italy. And the yellow that you see there is sulfur. And this is an element. Here it is, looking closer, just lumps of sulfur lying around. In fact, here's a boulder of sulfur. Now, sulfur has been known for hundreds and thousands of years. In fact, it's even mentioned in the Bible, but under a slightly different name. You won't find the name sulfur in the Bible. You'll find a different word for sulfur, and this was the word brimstone. So it says, for instance, that God rains fire and brimstone down on people. Okay? So brimstone, well, the name there literally means burning stone. Oops, and this is, it's just gone a little bit. Let's try it that way. So this is some sulfur here. I'm not going to set fire to my nice piece down the front there because the person who lent it to me might be upset. I'm going to see if I can set fire to this here. Ooh, if I can get it to float on there. Right, and that's steady. Right, so there it is, just floating away. And now I'm going to just apply a light and see if we can get it to burn. After all, the name brimstone means burning stone. So let's see if we can get it to burn. Oops. Well, I think it's burning there. And unfortunately, it gives out some rather choking smell, so I'll cover it up. And you'll notice that I've got a rose in there as well. And it's floating on some cabbage water. And this is because there's something I want you to see here. So we're burning the sulfur, and this means that the sulfur is combining with the oxygen from the air. So we could write a chemical equation for this. The sulfur is combining with the oxygen, and it forms a gas, sulfur dioxide. And with extra oxygen, it could even form another form of sulfur oxide, sulfur trioxide. But these dissolve in water, and they give acids. So sulfur trioxide dissolves in water, and it forms sulfuric acid. So at the start of the lecture, remember that was one of the chemicals that I used. I used some sulfuric acid. But this is how we can get our sulfuric acid. Now, once we've got the rose there, by the way, I'm hoping that you may see a change take place, because any sulfur dioxide that comes out here may react with the rose, and it can break down the structure of those pigments that colour the rose, so it might actually bleach it. And also the water here, the the purple cabbage here, it reacts with acid, and we get a red colour if there's any acid there. So keep an eye on it. We'll see what happens. Right, now, having got my acid, I can do things with this. For instance, some of these minerals react with acid, such as this beautiful green mineral here. Well, this is called malachite, and it's a copper carbonate. It's a type of copper carbonate here. And a test for carbonates is, well, if we add some acid to these, they should bubble. So let's try this. Let's take a piece of our malachite here. And we'll see if this really is a carbonate. I'm going to smash it up using my handy anvil. I'm sure the camera there doesn't like this, but never mind. Right, let's keep smashing. Okay, so now I've just got some bits. I'm going to put some of these bits into a tube here. I'm going to add some sulfuric acid that we've just made from our burning sulfur there. Put some sulfuric acid in and see if anything happens. Well, it is beginning to fizz. You can see little bubbles coming out here. Okay, and this is as our mineral, the copper carbonate, is reacting with the acid, and this is driving out some of the carbon dioxide. Again, we could write a chemical reaction for this. This is the copper carbonate is reacting with our sulfuric acid, and what we're making here is, well, copper sulfate, and this will have a nice bluey colour eventually, but we're driving out the bubbles of carbon dioxide gas. Now, really, we should test to see if that really is carbon dioxide, because there are lots of gases that there could be. And there's a nice chemical way of testing to see whether a gas is carbon dioxide. Now, one thing that we could do is just see if it put out a fire, because of course we use carbon dioxide fire extinguishers. But actually there are other gases that would also put out the fire, such as nitrogen. That doesn't support combustion. So there's a nice chemical test to detect the presence of carbon dioxide. And this involves, well, a new chemical. And this new chemical is called lime water. This is the one that we used before, remember. This is the alkali, the calcium hydroxide. This is dissolved in the water here. So this is our lime water. It's nice and colourless. I'm going to just switch on a pump that's going to draw some air through this funnel. So it's just bubbling away. Nice colourless solution. But what I'm going to do now is make some carbon dioxide. And I'm going to make it from the elements, from the oxygen around us, and from a little torch here, and from some carbon. So here is our impure form of carbon. So I'm just going to heat up the carbon first of all. So this is a nice way to get my barbecue started. Actually, I'll just have is there a shield, please? I'll just put that on. I'll just put a glove on as well, thank you. Thank you. Lovely. Just in case there's any sparks. So I'm just heating up the charcoal first of all. I'm going to turn the fuel off, and we're just going to use the oxygen to keep it going. I hope. Aha, there we are. So now there's no flame coming out the front here, it's just oxygen. So that's going to help keep my charcoal burning nicely. But at the moment, our lime water is completely colourless. But I'm now going to draw some of the gases that are coming off of the burning charcoal through our bubbler, and keep an eye on the liquid in the bubbler. Okay, so we're just drawing some of the gases off of this, and some of this is carbon dioxide. And I'm hoping that we should see a change take place in the liquid. I think you can see that it's beginning to change. It's not so clear as it used to be. It's beginning to get cloudier, okay? And this is as the calcium hydroxide that we have in there is reacting with the carbon dioxide. Oops, I'll just leave that there for a second if I just hand that back. Thank you. So it's certainly changed now. It's gone very, very cloudy. It's gone very white. Switch the pump off there. The chemical reactions that have taken place, well, we had the carbon reacting with the oxygen. So this was our charcoal, the carbon there, reacting with the oxygen that I was putting on this and the oxygen from the air. That gave us the carbon dioxide. But the chemical test for this was bubbling the carbon dioxide through the lime water here, which is calcium hydroxide. And the milky colour that you see there is due to a precipitate, fine particles of calcium carbonate. That's the test there for for carbon dioxide if it turns the lime water milky, this milky colour that we see here. But haven't I just used another chemical? What about this calcium hydroxide? Well, where does that come from? Actually, we can get it from the calcium carbonate, because calcium carbonate can be found lying around. In fact, well, here's a lump here. This is limestone. Limestone is made up from calcium carbonate. This is a lump of calcium carbonate, and we can build buildings from it if we wanted to. But this in turn is made, we can find this when sea creatures have fallen to the bottom of the sea over millions of years, become compacted. Well, this is essentially what this is made from. It's made from shells and skeletons of sea creatures. This is made from calcium carbonate. And I can show that because, of course, well, we've seen that carbonates react with acids, and we get bubbles of carbon dioxide given off. So I'm going to try this now. I'm going to take one of these shells. So let's take the shell and a couple more shells. Take it over to the anvil. And we're going to smash it up. Let me just get those bits off. So I'm going to smash up the shell. Put the bits in there. More bits. Oops. And this nice looking shell. All right, plenty of bits now. So if this really is a carbonate, again, it should react with an acid to give bubbles of carbon dioxide. Well, let's see if it works, shall we? I'm going to use a different acid, this time nitric acid. So adding this to our shells, well, certainly very bubbly. Oh, very, very bubbly. Oops, extremely bubbly. And it's bubbling over the top, never mind. So the chemical equation for this reaction taking place here is the calcium carbonate is reacting with this acid, in this case it's nitric acid, and we're forming, well, calcium nitrate, but the bubbles of carbon dioxide we can see here oozing over the top. Never mind, right, we'll just leave that bubbling away, I think. But there's another way that we can drive out the carbon dioxide from the calcium carbonate that the shells are made up from. And we can do this just by heating it up. Okay? So, well, this block here is made of our calcium carbonate, but I've got another block somewhere down here. Let's have a look. So, and this block, well, it looks just the same, but this block is, we've heated this up overnight, and we've driven away the carbon dioxide just by heating it. So, oh, I've got my donkey back, that's not good. Need to get back to where we were. So we've heated up the calcium carbonate and driven away the carbon dioxide, okay, away from the what we've got left, and what we've made is, nearly there, what we've made is calcium oxide. So heating up calcium carbonate drives out the carbon dioxide and leaves behind calcium oxide. Now, looks just the same though. How would you know? Well, actually, one way you know is this is quite a bit lighter than this one. Because we've driven out the carbon dioxide, it's actually not as heavy per the same volume. If we had the same volume of this block and that block, this one would be lighter. But there's another difference as well. Watch what happens when I pour some water onto our limestone, onto our calcium carbonate. Okay. Now pay attention. Can you see what's happening here? Nothing. Yeah? Nothing's happening at all. Well, this is very good, of course. I mean, what we've got now is a wet rock. Okay? But this is important because, I mean, after all, we make buildings out of this, and it would be pretty bad, wouldn't it, if something did react every time it rained and our rock just disappeared. Of course, if I'd used acid, well, we've seen what happens with acid. It bubbles up and it would dissolve. So this is why acid rain is very bad. If there's, for instance, any sulfur that's burnt into the atmosphere, that sulfur can form acids and that would dissolve our rock and that would be pretty bad. Okay, but on the whole though, the rock does not react with water. But what about this rock? Well, let's see. I'm going to just pour some water onto this one and we'll see if anything happens here. So what have I got? Well, it looks like I've just got my wet rock again. Nothing very exciting has happened at all. But actually, look, something is happening. It seems to be smoking. Well, this is actually steam coming out. And this is because there's a very violent chemical reaction taking place here between the calcium oxide and the water. So it looks like it's alive. It looks like it's changing and growing and changing over time. So this is why it's called quick lime. So this was limestone, this is quick lime. Quick there means, well, it means living. Just like the quick of your fingernails, it's living tissue here. This quick lime is alive, it's reacting with the water. And the chemical equation for the reaction taking place here is, well, the calcium oxide that we've made by driving the carbon dioxide out of the calcium carbonate. The calcium oxide reacts with the water and we're forming calcium hydroxide. So, very, very different from our rock here. Calcium oxide, which is what we made, reacts with water and forms calcium hydroxide. That is our lime water. When we dissolve it in water, we get our solution of calcium hydroxide, which is the lime water. Well, there is another way that we could make some calcium hydroxide, and that's starting from calcium metal. And I have some calcium metal over here. Actually, this is very old calcium metal, so I can use it up for this. It's been in their stores here for tens of years. Okay, so it looks almost metallic-like. I'm just going to add some water to this. So this is my calcium metal. I'm going to add some water. And, well, if this was fresh calcium metal, it would have already begun to react, but it's taking a little bit of time. We'll just leave it there. This is taking a little bit of time because it's so old. And this is because, well, over time, calcium metal reacts with oxygen from the air, and it would form calcium oxide. There's still some calcium metal left, and that is now beginning to react with the water as well. And the chemical equation for this is the calcium reacts with the water and gives out bubbles. Now, this isn't carbon dioxide. There's no carbon in this. These bubbles are now hydrogen. The hydrogen's coming from the water, okay, reacting with the calcium. So we're getting bubbles of hydrogen here, and we're getting, well, a white solution left, a white precipitate forming. That, again, is calcium hydroxide. But the important point is, because this calcium, okay, reacts so quickly with water, or even with air, this means that we can't find calcium metal lying around in nature. Now it's going quite nicely. So we can't find calcium lying around because it's too reactive. We can't find any metals that are too reactive because they will react with the oxygen or with the water that is all around us. So if we do want to find some metals, we would need to find something that's less reactive. We've seen that iron is perhaps too reactive. Well, one metal that's not quite as reactive is copper. And here's some copper here. We can find this, but even this is really hard to find. We need to look in places where it's not too wet and it's kept out of the atmosphere if we want to find pure copper metal. And this is because copper will also change over time. And I thought I'd show you this. Well, I went up onto the roof of our chemistry department back in Cambridge, and the roof is made of copper. Okay, so here is copper, here is our roof. Now, it doesn't look the same, does it? And this is because the copper has reacted with the carbon dioxide, with the water in the air, and it's changed, and it's gone this green colour. Well, I thought I ought to prove that it really is copper, so I went up onto the roof to do a spot of vandalism. I went up onto the roof with some sandpaper and rubbed away on the surface, this green colour, rubbed it away, and then underneath it really is copper metal. Okay? So just over time, the copper changes by reacting with the gases that are in the air, reacting with water, and what you get is, well, essentially you get this mineral here, which is the malachite, a type of copper carbonate, hydrated copper carbonate. And that's what makes the roof look green. Okay, so what if we wanted to get the copper out of our mineral? If this is how we normally find our copper, how can I get the metal out of it? Well, this is what I'm going to try now. See if we can get some copper out of our mineral, out of the malachite. So I've got the bits that I smashed up earlier. I just smashed them up a little bit more. That's it, into a nice powder. So I'm just going to take this copper malachite here, this copper mineral. I'm going to put it onto some of the block of charcoal here. Just pick a nice one. Actually, let's use this one. So just going to pour our powdered malachite onto the block. Thank you. Thank you. Now I'm going to heat this up. Now remember, when we heat up the calcium carbonate, we drive out the carbon dioxide. And the same thing's going to happen with this carbonate. Heating it up will drive out the carbon dioxide, and that's going to leave, well, not calcium oxide, but copper oxide this time. And this is the chemical equation on here. So the calcium carbonate, heating it up, driving out the carbon dioxide, and we're left with copper oxide. And you may see a change taking place because the copper carbonate is green, but the copper oxide is black. So watch for a change. So you can see that it's beginning to change and go black. Now, why am I heating it up on the charcoal though? Why am I using the carbon here? Well, at the moment then, if we heat up the copper carbonate, we're just left with the copper oxide. But what we're trying to get is copper metal. And we need something to take away the oxygen from the copper oxide. And this is the role of the carbon here, because we know that carbon reacts with oxygen to give us carbon dioxide. So hopefully, if I heat up this a little bit stronger, we should be able to steal away some of the oxygen and using the carbon there, and just be left with the... I'm not quite sure if we're there yet. Just keep going. I'm trying to see if we can get some copper metal. Certainly got something. Right, now I'm going to fish this out and put it into a little bit of acid in a minute. I just need my tongs over here. That's good. Thank you. So at the moment this is still hot, and of course it may react with some of the oxygen from the air. So I'm just going to put it into some sulfuric acid, and that will dissolve away any of the remaining copper oxide. Oops, there it is. Where's it gone? And that will get rid of any, if there is any copper carbonate left. So this is the piece that I've just added. And you can see, I think, that what we've got now is a nice piece of copper. It's not still a little bit mucky, but here's a piece that we did from the previous lecture. Okay, and you should be able to see that what we've got there is copper metal. Okay, and that has just been made from the naturally occurring copper mineral, the malachite. Okay, the copper carbonate. So we heat up the carbonate, drive out the carbon dioxide, make copper oxide, and then we use the carbon there to steal away the oxygen from the copper oxide to leave the copper metal. And that's what we've made. And this is one of the easiest metals to make. Okay, because copper is so inert, it doesn't hold on to the oxygen really strongly. It's quite easy to take it away. And this is why it was one of the first metals that was ever prepared from its ore. So after the Stone Age, when people were just using stone tools, came the Bronze Age. Or, well, the bronze is mainly made up from impure copper, okay, because it's one of the first easiest metals to extract out of the ore. And of course, once we've got our copper metal, we can make all sorts of useful things, like this pot, for instance. So this is made of copper. We can clearly see it's a nice copper pot, and we can use this for cooking. But actually, if you do use it for cooking, you need to be very careful, because copper is actually poisonous. And so any copper pots that you use in cooking, well, they're actually lined with another metal inside. Now, this one has been very poorly lined, and it's because it's very old, and it's actually changing. So it looks nice and shiny on the outside where it's been polished, but inside, well, we can see traces of this other metal, but it's also, we can see traces of green. And this is where the copper has been exposed, and it's reacting with, well, the oxygen, the carbon dioxide, and forming our green mineral again. Well, I've put some pickled onions into this pot. I don't know if you can see them in there, if you can see the pickled onions in the bottom of the pot. Oh, yes. Okay, so just pickled onions in their vinegar, but actually they're going nicely green. And this is because of the copper mineral is dissolving in the acid in the vinegar here, and it's giving rise to copper ions in the solution. Now, we need to be very careful of that, because this would be poisonous. And, well, I can show this. I'm going to see if we can just get a little bit of the solution out. So we just pour a bit of our pickling solution out of here. And I promise you, all I've done is just put the pickled onions into the pot. But you can see that it's quite green already. Now, actually, in times gone by, this has been used to colour food. Okay? And this is a book published in the 1820s where it was talking about some of the poisons that were used to colour foods. Because copper, it is poisonous, copper ions here. So it'd be very bad to eat these poisonous pickled onions now. But this book here tells you about the poisons that we use to colour foods, but also methods of detecting these compounds. And this is very important because, as I say, they're poison, and that means that, well, as it says on the cover of this book, it says, there is death in the pot, okay? So this pot here has death in it. We need to detect the poison here. But it tells us how to do this. It says, if we take some of our solution, so I'm just going to take a little bit of this solution here, and if we add some ammonia, this is what I've got here, ammonia solution, well, adding the ammonia to the solution that we suspect of containing copper, we get a beautiful dark blue colour. And that's as the ammonia is interacting with the copper ions that are in the solution there. And we form this complex that has a beautiful, beautiful dark blue colour. That confirms the presence of copper, tells us not to eat our pickled onions. Okay, but I've just used a new chemical. I've just used some ammonia, okay? Well, where does this come from? We have to make our ammonia then if we want to use this. This is meant to be chemical free. Well, how are we going to get our ammonia? You get ammonia from urinating camels, okay? So this is what we have here. Well, actually that's not quite true. It's not just urinating camels. It's any urine would contain nitrogen. Okay? Because we need nitrogen. It's in our amino acids, it's in the proteins that make up our bodies, and we need to excrete this surplus nitrogen. And this is what the camel is doing, okay? But now the reason I've got the picture of the camel here is because, well, underneath this it says making sal ammoniac, or salt of ammonia. And this is, well, it's an ammonia compound, ammonium chloride, and it was made by taking the earthy substance underneath the camel there, mixing it with salt and heating it up, and out comes this compound. But you don't need to use urine. You could use any animal waste matter. So, for instance, well, this is a little deer, and it's called a hart, and even from its horns, the horns contain lots of proteins. We can use those to prepare ammonia. In fact, an old name for ammonia used to be called spirit of hart's horn. Okay, so that's a hart, and from its horn we could prepare ammonia. And in fact, I have a bottle here, this is at home, that says hart's horn ammonia. Okay, well, I thought it'd be nice to try and do this, see if I could make some ammonia to show you from some horn. The horn of the hart there is actually made up of lots of hair. So I thought, well, I'll start from hair. And this is what I did. I took some horse hair, and that's what that is. It's just lots of hair from a horse, put it in a flask. But now I can't, unfortunately, show you this demonstration live because it's one of the worst experiments I've ever done. Okay? Absolutely hideous. Because, well, you know what happens if you singe some hairs? It smells really horrid, yes? Then that's just a few hairs. Well, imagine all of those hairs if you heat those up. The smell is absolutely disgusting. We did this in a fume cupboard in the laboratory, in the labs back at home. And actually, even though we did it in a fume cupboard, the smell escaped and it drove all the students away. So I can't possibly do it here because it would clear the lecture theatre. But nonetheless, so this is what happened. So we heat up the hair, and this is how it went, like that. Going to this gooey, disgusting brown mess. And you keep heating it up. And what we're doing here is just breaking down the complex structure of the proteins that are in the hairs, and we're forming, well, things that are just lower in energy, more stable. And what we get, we heat up this, and remarkably, you get a nice white smoke coming off. And this white smoke contains ammonia in a compound. This is ammonium carbonate. So we've broken down the complex organic structures, and we've ended up with a very simple inorganic structure. This is ammonium carbonate. And, well, I sent this to be analysed, and this is using a technique called X-ray crystallography, where you shine X-rays at crystals, and this reveals where the atoms are in the crystals. And this is from my distilled hair, these crystals that came off, and the black represents carbon, the red oxygen, the white's hydrogen, and the blue is nitrogen. So you see the blue with 4 hydrogens around. That is ammonium. It's a positively charged ion, and it's sticking together with these carbonate ions, but we've made it. And actually, the person who analysed this and recorded the crystal structure was really excited because it was a new way of packing together these ions, and it had never been discovered before. So he was very, very excited and thought we should publish this structure. But anyway, now, ammonia is very, very interesting. Now, I thought I should show you some ammonia, and I have some in this jar. We have some ammonium carbonate. And one of the strange things about ammonia, it really smells quite intensely. So All you need to do, I'd like you to experience this for yourselves, okay? You just need to hold this very carefully and then just push down on the rubber, and there's a little hole there, and you'll get a whiff of ammonia, okay? So you can smell what ammonia is like, okay? So we'll pass this, I'll pass this over here. So here, if you'd like to try this first of all. So just take the whole thing, and just cautiously push down and smell, and see if you can smell it. Did you smell it there? Oh, you've got to try it, you know what you're missing. Okay, we also have another one. We'll pass this one round over the sides here, so if you just want to try that one. Okay, so now while that's going round, I'll show you some more reactions of ammonia. So ammonia itself is a gas, okay, and that's what you can smell. You can smell the gas coming off there. Now I've put some of the gas into this tube, and ammonia is lighter than air, okay, so it can stay in the tube even if I took the top off. And actually I need a rose. Can you just hold that for me, please? Okay. So I'm going to add a rose to the ammonia, and let's see what happens to my poor little rose. Okay, so the ammonia is in the tube, and it's lighter than air, and this is because it's only got one nitrogen atom and 3 very, very light hydrogens, whereas air, of course, has 2 nitrogens combined together in N2. Just going to shove the rose in and put the stopper back on. And remember, the colours of the roses are due to these dyes, these anthocyanins, and they react and change colour. And the poor little rose here, you can see, is changing, and it's getting darker and darker. Okay? So the rose here is acting as an indicator. It's reacting with the ammonia, showing that it's not very acidic. Okay. Now I have some more ammonia in this flask. And I'm going to show you one other experiment here. Maybe we'll collect the ammonia back and then hand that out later, and you can smell it on the way out. Should we do that? So that'll perhaps be... Okay, so this flask is also filled with ammonia, and it's lighter than air. And I'm going to swap the stopper here for another stopper. Here it is. And this stopper has a tube running up through it. Okay, I'm just going to put this back into the clamp here. So the tube is now going into the water at the bottom. Now I'm going to squirt a little bit of extra water in, like that. And the ammonia is very, very soluble in the water, so it's dissolving there. And this is reducing the pressure in here, which means the atmosphere is pushing the water up the tube. But we've added some cabbage indicator here, and we've added a few drops of acid to make it red, but now it's reacting with the ammonia and it's changing green, okay? Showing again that the ammonia is not an acid. It's the opposite of an acid, it's an alkali, okay? So this is a rather beautiful experiment here. It's called the Ammonia Fountain, okay? Very, very nice. Now ammonia, though, gives us a chance to make new compounds that contain nitrogen. And one of these that's really, really nice and very, very fun is a nitrate. Nitrates are good fun. And, well, I needed to find some naturally occurring nitrates. And again, we're going to make use of the ammonia that's formed from, well, the decay of animal urine. So I went back to my father's farm and went to a stable that hadn't had the animals in for quite some time, but all of the nitrogenous waste there, the waste containing nitrogen, has been decaying, and it formed some ammonia. But this is changing over time. It's oxidizing. So bacteria and so on, these organisms can change the ammonia and add extra oxygen and make nitrates. Okay? And, well, these are beginning to, they look like they're growing on the wall of the stable. So the white mineral that you see there, this is where the nitrate is reacting with the minerals in the bricks and forming, well, it's potassium nitrate. And this also used to be called saltpeter. And Peter is my name. Is there anyone else here called Peter? Do we have any other Peters? Am I the only one? Oh. Well, Peter, my name, means rock. And so saltpeter literally means this is a salt that's forming on the rocks. And we can see this now. Why this is because the oxidation, the change of the ammonia to nitrates reacting with the minerals from the rock forms nitrates. Now all I did was just scrape off some of these crystals that were growing on the rock there. scraped them off and sent them for analysis, and they proved to be, well, more than 90% pure potassium nitrate. And the reason I really wanted the potassium nitrate is because we can do some fun things with it. Now, one thing that we can do, we can make the nitric acid. Remember nitric acid we needed? Well, we can just make that from nitrates and sulfuric acid. But I wanted to do something more fun, and that was make some gunpowder, okay? So, gunpowder is a mixture of potassium nitrate, or saltpeter, and sulfur, which we find lying around, and charcoal, which we can make just by partially burning some wood. Now, I have some gunpowder here, and I'm just going to sprinkle it on this spoon. And I have a little spirit burner, and I'm going to light the little spirit burner. And put it underneath. Now I have another spoon over here, and this one has, well, slightly different ingredients. This one has, it's not black, this one is yellow. It's a different mixture. We've missed out the charcoal. And instead, on this one, it's a slightly different mixture. Instead of the charcoal, I've put some potassium carbonate. So this is yellow powder. And again, we're going to do exactly the same thing. Just put the little spirit burner underneath to heat it up. Now, we all know, of course, that gunpowder is used to make fireworks, to make rockets and bangers and so on. But so we're going to keep an eye on these two now. So on the left-hand one, this one here, we've got our gunpowder. In the right-hand side, we've got the yellow powder. Gunpowder, charcoal, burnt wood lying around, saltpeter, scraped from the stable wall, sulfur, okay, find lying around near volcanoes. The yellow one, we've just swapped the charcoal for potassium carbonate. Now, I need to warn you, if you're very sensitive and you don't like loud bangs, I suggest you put your fingers in your ears, because we know what happens with gunpowder, okay? In bangers, it can go bang. So just keep an eye on this one. Just watch it very carefully and see if it goes bang. And watch the other one, the yellow one as well. See if it goes bang. If you don't like bangs, fingers and ears. Okay, might be quite loud. Fingers and ears if you don't like them. Okay, now we need to just see how it's going. Well, it's beginning to go. Heating nicely. Watch carefully. Okay, you need to see which one goes bang the loudest. Or maybe neither of them will go bang. Or perhaps they both will. Oh, well, there's the gunpowder. That didn't go bang at all, did it? But the yellow powder hasn't gone yet. So let's see if that one goes bang. So the yellow powder, just the same. We've just replaced the charcoal with potassium carbonate. Oh, maybe it's going to go. Can you hear it crackling? Yeah. Okay, so now that was actually very, very interesting because, well, we know that we make bangers out of gunpowder, but the gunpowder didn't go bang at all. And that was because it wasn't confined. In order to get this explosion, a bang from the gunpowder, we need to wrap it up, tightly confine it. And this is so that the chemical reaction can move through the mixture faster than the speed of sound. That's what gives us the bang. But the yellow powder, now this is really quite remarkable. This is one of the few substances that is known that if you just heat it up, it will detonate with a loud bang like that. Not many things do that. This is quite remarkable. But anyway, right. But I've used another chemical though. I've used potassium carbonate. So where do I get that from? Well, I can get that from ash, from wood ash. And this is what I've got here. So if you completely burn up the wood, the charcoal, you're left with this solid residue. This is just wood ash. And because it's a carbonate, remember, what's the test for carbonates? What happens when we add acid to carbonates? What happens? Anyone remember? Yep. It fizzes, yes. And why does it fizz? What's the gas coming out of the carbonate? Yep. Carbon dioxide. Well, let's try it then. We'll add some nitric acid to our ash. And yes, it's certainly fizzing away. And this confirms that there is a carbonate there. This carbonate is potassium carbonate. There's some of that in there. In fact, so the reaction there, potassium carbonate reacts with our acid. This was nitric acid. We get potassium nitrate. Well, that was our saltpeter that we used in our gunpowder. And carbon dioxide, the bubbles that we see. Okay? In fact, this is how we get the name potassium. The name potassium comes from, well, this substance that we can extract from the ash, from this wood ash. Okay? This is potassium carbonate, known as potash. And so what we see here is a chap, he's burning some wood, making ashes, putting the ashes into a pot, stirring them around, extracting what he wants, the potassium carbonate, this potash. And so potassium gets its name from potassium carbonate or potash that was used to make the potassium in the first place. But there's another element that was first discovered from ash, not wood ash, but ash from this stuff, from seaweed. Okay? Now we thought we'd try this. So we took some seaweed and we completely burnt it into ash, and then we dissolved, we added some water, got a thick sludge, and then we filtered it. So now we've got this brown solution. And so this is our gooey seaweed ash with some water. I'm going to add some acid to this. Okay, so add some acid. Now I'm going to add something else, some hydrogen peroxide. Now this is used to convert any of what I'm looking for, which is, I'm trying to find some iodine. But in the seaweed, it's not there as iodine, it's as a negatively charged ion, iodide. And the hydrogen peroxide here releases the iodine. Oops, my seaweed's falling out. So just give this a bit of a swirl. Now unfortunately we can't see any iodine yet, so I'm going to add some hexane. This is basically from petrol, so I'm going to add this. And the iodine, if there is any here, it should dissolve, it should move from the water layer, the lower layer, into the top layer of hexane. And I'm hoping, I think we can just about see this, that the top layer is becoming pink. Okay, so perhaps if we put a piece of filter paper behind, I'm hoping that you can see that there's a slight pink colour there. And that's due to iodine that we've just made and extracted from our seaweed. Now, in case you can't see the pink colour there, we're going to make a little bit more iodine for you so you can see. Now, in the corner here, I've got a very, very reactive compound called nitrogen triiodide. And this has nitrogen combined with iodine. And it's very, very unstable, though. And we can release this iodine just by touching it. Okay? But I need a volunteer to help. I see we have some volunteers. But the volunteer needs to be very, very good at basketball or netball. So does that narrow it down? Who's, oh. It looks like there's somebody at the back there with the white sleeves. Yes, you want to come down. You look very, very keen. Very good at this. Yeah. Okay, right. Do you want to tell us your name then, please?
Nessie.
Okay, and you're really good at netball, are you? Or basketball? Which one? Netball. Okay, right. Now, what you need to do is, first of all, you need to put on your safety spectacles. You can have the same ones as me, nice yellow ones. And then you need to put on these ear defenders, so then we can talk about her and she won't hear. Okay? No, sorry, just kidding. I'm going to put some on as well, actually. But now, what you need to do is take one of these ping pong balls, take one of those, and you see that container over there. I wonder if you can throw the ping pong ball into the top. Now, hold on, before you do that, I just need to put my ear defenders on, and I need to warn everyone that if we succeed here, there may be a loud bang. There will be a loud bang, and you may see some purple colour, so keep your eyes open. Okay, right, you feeling confident, feeling ready?
No.
Yep. Okay, right, see if you can do it then. Into the top of that. Oh, good shot. Oh, it needs to land on the paper, and it's, didn't quite get on the paper, but a very, very good shot. Okay, try again. Oh, okay, I'm very impressed, by the way. I couldn't do this. Oh, good shot. Oh, it's bouncing round it, isn't it? It's not bouncing on the paper. Try again. Good shot, though, good shot. Ah. Nearly. Keep going. Oh, no, I can't believe it. Try again. Oh, missed that one. Oh, and that one. Okay, we'll try that one again, yeah. Oh, okay, I think someone will fetch that one for you.
Do you want to have a try?
No, I wouldn't do it. I wouldn't be able to get it in. You're doing much better. Oh, dear, that one dribbled over the top. Keep going. Oh! Well done. Fantastic, excellent shot. Thank you. But look what you've done to my ping pong ball. It's dead. It's destroyed. Okay, so yes, a very violent reaction took place there. But notice the purple colour, and that purple colour that you see there is iodine. Okay, so it's iodine molecules, I2, floating around. Now actually, this is quite nice, the iodine. We can use this in a nice chemical test. It reacts with starch, so this potato has starch, to give a nice sort of purple colour, a nice sort of blue-black colour. So I've got some iodine here. It's dissolved in alcohol. I'm just going to dribble some onto the potato here. And initially it's brown, but as soon as it comes into contact with the starch in the potato, we get a very dark blue-black colour. Okay? This is a reaction between the starch and the iodine here. Starch is actually, it's another chain of all these glucose molecules joined together. But anyway, right now, what can we do with this? Well, I've got some water here. I'm going to add some of the iodine to the water. Now this one isn't purple, by the way, and that's because the iodine is interacting with the water in a different way. It's the free iodine molecules that have that nice purple colour. With some water here, it's a sort of browny colour. Now I'm going to add some starch, though. This is like from the potato, and we get that nice bluey black colour. Good. Right, now I'm going to add some sunflower oil. Okay, and this is just fat. So I'm going to pour this onto it. And of course, we know what happens when we pour oil onto water. They don't mix together. The oil floats on top. So the oil is floating on top. Okay, now, so we've got our oil floating on top of the water that contains the iodine and the starch. I'm just going to mix these together, and you should see a change take place. The blue colour has disappeared. Now, why is that? This is very, very interesting. It's all to do with the type of fat or oil that we're using. Now, this is a model of fat. There's all sorts of different fats. We've got fat in our bodies. We've got fat from lard, or this is fat, this oil here. This is what it looks like. It's got these long dangly bits joined up. Now, it's the long dangly bits that are interesting. These long dangly bits are chains of carbon atoms. So this chain here, every carbon, apart from the end one there, everyone in there has 2 hydrogens stuck onto it. Well, that's what we call a saturated fat. Okay? But we also have unsaturated. You know that they might be better for us. And where is an unsaturated? This one is an unsaturated one. So what that means is that there's a carbon in the middle here that has, well, it's a double bond with the carbon. So the carbon is joined with 2 bonds rather than 1 between the carbon atoms. It means it's only got 1 hydrogen on it. Okay, so now this is the interesting thing. It's these double bonds, the carbon-carbon double bonds that react with the iodine. Now I have a little slide here to show this. So here's our fat, and there's the double bonds on top, and these react with the iodine. So here comes some iodine, and it sticks onto these double bonds. And once it's stuck on, it's lost its colour. Okay, so that's what's taking place when we mix the fat with the iodine there. It's sticking on. Now, why is this so important? Well, saturated fats, without those double bonds, they wouldn't do this. And those saturated fats are bad for us. You may know this already. Why is that? Well, these saturated fats, these nice long chains, these nice straight long chains here, they fit together very nicely. And that gives us harder fats, like lard. We can also have trans fats. This is a trans fat, so we have a double bond, but you would hardly know looking at this that there was a double bond. There it is. If I look at it like that, you wouldn't know. They still fit together very, very nicely. But we can also get double bonds that make a kink in the chain. And this is not I'm trying to unwrap my fat. Anyway, there we are. So here we have a double bond, and this has put a kink in my chain now. The double bond is here. This is not a trans fat. This is a cis fat here. And this is better because it doesn't fit in so well with these saturated fats or the trans fats, and this keeps them more liquid. Why is this important? So, well, of course, this is a liquid fat. This one, oops, I've broken it. This one is a liquid fat, okay? But it's better for us because it doesn't clog us up inside. This is the clog that you get in your bodies if you eat too much saturated or trans fats. This is actually taken from inside the artery of somebody's leg, okay? This is quite big. It's a centimetre in diameter. And what's happened here, all the fat has lined the arteries, and it's made it very narrow for the blood to try and be squeezed through. And that means you need a stronger heart, increases your blood pressure, okay? So your blood pressure goes up, that puts a strain on your heart, you can have a heart attack, you can even die. So we shouldn't eat too much saturated fat or trans fats. But we can detect these trans fats using our iodine, which is nice. Now, unfortunately, my fat has fallen to pieces, but this is actually a good thing. We can do this, and we get some interesting things, because if we break up our fat, and we can do this by adding some alkali, like potassium hydroxide, what we get here is this dangly chain. Well, the bit on the end here, the dangly chain here, it's still like sticking in oil, but this end, with 2 oxygens on it, like sticking in water. So what we've made here is, well, it's a detergent, it's soap. So by breaking up our fat, what we get is, well, this is one bit of soap. We can get another bit of soap from this bit here, break up this bit, there we are, more soap, okay, more soap, and the other bit that you have left, well, the bit that they were all joined up to is this bit, and this is called glycerol, okay, this is glycerol, and this is actually quite fun, because this is something that we can change, we can chemically modify the glycerol that we get just by breaking up fat, so we can change it by adding extra nitrogen, extra oxygen, and we convert our glycerol into nitroglycerol, or nitroglycerin, which is the key ingredient of dynamite. Okay? Now, I thought I should show you some of this. So I just need to put on my safety protection. I need my ear defenders, please. Yeah, those orange ones, thank you. Okay, so this is very, very dangerous. This is what we have in dynamite. Okay, so I'm just going to put on my ear defenders, going to put on my mask here. And I'm just going to get a piece of paper. I'm just going to put my paper down there. So this is my nitroglycerin. That's okay, I'll just leave it there, thanks. This is my high explosive, my nitroglycerin. Just a tiny, tiny drop, just a few drops. Put it onto the paper that's just sitting there. Okay, hardly any at all. Okay, I think we need to take this away because it's so dangerous. I'll put the top back on that, and I shall give it to Vance to take away. Thank you. So you might be able to see it just here. Here it is. This is the little drop. It looks like sort of grease, essentially. So the drop of nitroglycerin. Well, what should we do with that? We'll hit it with a hammer. Right. Okay, so see if I can hit my nitroglycerin with a hammer. Certainly very, very reactive. And yet, this nitroglycerin is actually used to treat heart problems, so it's used as a medicine. So here, it says glycerol trinitrate, well, that's the proper name for nitroglycerin, and that's used to treat people who have problems with their hearts and high blood pressure. Okay, so amazing. But the reason that it was explosive was because of all the nitrogen and oxygen that was built into the structure. And this is common for many explosives. So we have TNT at the top there, trinitrotoluene. We have nitroglycerin. We have these other compounds here that make up high explosives. All have lots of nitrogen and oxygen built in. Well, this just about brings us to the end of the lecture, but I just thought I'd finish with, well, just showing you what this is all about, this extra nitrogen if we build it in. Remember I started off the lecture with filtering our coffee, and we filtered it through the paper, which was made of cellulose. So here's cellulose. Well, we can treat this. We can add in extra nitrogen and oxygen. We do this by treating it with sulfuric acid that we can make from our sulfur that we find lying around near volcanoes, treating it with oxygen, dissolving it in water, get our sulfuric acid. With nitric acid as well, we get our nitric acid for scraping stable walls to get our saltpeter. Okay, so that's how we get those. Treat this, and we end up with something that looks just like cotton wool, feels just like cotton wool. Nobody would know the difference, but just what happens if I apply a light to this? So watch it, now you see it. Oops, now you still see it. Now you see it. Now it's gone. Okay, now, so that's by locking the nitrogen and the oxygen in. But we've also seen some gunpowder. We put some gunpowder on this track here. Now remember though, that the gunpowder was actually a mixture. So the nitrocellulose, that was a chemical where we'd locked in the nitrogen and the oxygen into the chemical structure itself. We changed the chemical structure. With gunpowder, it's just a mixture. We've mixed up sulfur, we've mixed up potassium nitrate, we've mixed up some charcoal. And, well, it burns fairly quickly. This is professional gunpowder. And, well, let's see how quickly this one burns. Pretty good. We've got a nice whoosh of smoke there. But we haven't used professional gunpowder on here. This is just gunpowder that, well, Mark made this one. Mark, do you want to give us away? Mark made this. It's not quite as good as the professional stuff because he hasn't made a really intimate mix with the sulfur, the charcoal, and the saltpeter. But, and it's all in the mix that we get a really good burn. So I want to show the difference between just mixing things coarsely and, well, locking it into the chemical structure. So we've got some compound here where we've some nitrocellulose. So I've got some nitrocellulose in here. This is, remember, where we've locked in the extra nitrogen and oxygen. So here's cellulose, here's nitrocellulose. And so I'm just going to put some of this on the track. And it's a little bird. There we are. Okay. We'll put him there. So he can... So here he is. So he wants to watch the all the fun and excitement that's going to happen. Right. Okay. Right, so now we've got our little birds. So they're made of nitrocellulose. We're just going to light our pour gunpowder. So this is burning very, very slowly. Okay, but that increases the suspense. Gives the bird something to watch. He's very excited. Okay. Thank you very much. Thank you for coming along. Thank you.